had mentioned this before when we first got started with electric and magnetic fields, is I tried to compare and contrast them. And I'm going to write that statement down one more time. With electric forces, these are caused by positive, negative interactions, and they do not require the motion of the charges to act. That doesn't mean that the charges can't move. Okay? We can still get an electric field even if the charges are moving, of course. But the motion isn't required for the force to act. Different with magnetic forces. What we need to have here are moving charges interacting with other moving charges. So the motion is required. For magnetism to exert forces. Okay, so that being said, we could look at the magnetic field pattern for this long straight wire. And the way that we can look at that is by just taking a kind of a clear table here and sprinkling a bunch of iron filings on it. If we do that, the iron filings will align in concentric circles that surround the current I that's flowing up through the plane of the board. And so it's pretty clear there that we have moving charges. And that's what's generating that magnetic field. But what about in this situation? Say we have a north and a south pole of a bar magnet. We have what are called magnetic field lines. That's what these are too. These directions in which the charged particles are aligned is the same as the magnetic field pattern. So this is one set of moving charges creating a magnetic field. And the other one then interacts with that magnetic field. So one charge, or charges, produces the magnetic field. Then a second moving charge feels the magnetic field and gets a force exerted on it. And that's when the force is exerted. So this seems a little bit mysterious then, because here I can see where the motion is. But here, this is the magnetic field pattern around a bar magnet. And this is something you may have seen before. We'll have this set up in lab for you this week so that you can see how that works with iron filings and how they can produce that kind of field pattern. We might notice that that might remind us a little bit of the electric field pattern for a dipole. It's very similar to the electric field pattern for a dipole. But here, we have to wonder, where's the motion coming from? If I've got this magnet here. It says north and south on it. And so I'm assuming there are magnetic field lines coming out of this horseshoe magnet, just the same way as there would be out of this bar magnet. With the horseshoe magnet, the field pattern might look more like this. North, south, and you'd have magnetic field lines that would go from north to south. That's kind of like what the electric field lines do, going from positive to negative. And we call one of these magnetic field vectors B. So magnetic fields are a vector field just like electric fields are. And this is some kind of a distortion in the space that's produced by those magnetic poles that go from north to south. So the big question then is, if we just stated that you have to have moving charges interacting with other moving charges, then where is the motion in either of these cases? It seems like it's just sitting there. Anybody want to take a stab at that? Where is the motion that might be causing the magnetic field? Now here, I think it's obvious. We've got a current of wire, and so that means that we have electrons moving in a certain direction. And so that's generating a magnetic field that ends up being concentric circles that surround the wire. But what's causing it here?
There would be motion inside the magnet.
Good. We have internal motion inside of the atoms themselves. And this is something we'll study a little more in Physics 2.8c. We're going to solve the Schrodinger equation, and we're going to look at all the different energy level values that are allowed, and you get substances that are what are called ferromagnetic, like iron. And so those substances have a coherent kind of a motion in their outermost electrons. The electrons themselves are spinning, and so you can think of the electrons themselves as being a bunch of little current loops that are spinning around and generating a magnetic field. And so each one of these is going to spin and generate a north-south polarity, and then that's going to exert torques on other atoms that are nearby, and that'll get all of those little, it's mostly the spin that does this and not the orbital motion of the electrons. But there's the motion of the electrons inside of the atoms that start to line up with each other in order to produce the magnetic field pattern. So there's still motion, it's just hidden. Okay, so that shows us that there is at least the possibility for generating a magnetic field from object that seems to be motionless. Now here, I'm going to get electrons moving from this cathode ray tube. I don't know if everybody in the class can see this very well. I may have to turn this a little bit.
Oh, got me in the eye.
What?
Got me in the eye.
Oh. Yeah, well, I think the fluorescent screen should protect you, Mark. But something does seem to have happened here, a little troubling. It's not in the center anymore. It could be that in one of our lab exercises we magnetized the frame a little bit. Think that may have happened? Okay, go ahead and turn that on. Okay, so as I bring this in, if the north is on the right and the south is on the left, then the magnetic field lines are going to go like this, out from the north, and then into the south, so it should be from your right to your left. Okay, and then the electrons are coming out this way. So let's bring this in and look at that. Can we see that? Everybody seen that? As I move this thing in, that's generating a force on those moving charged particles, and that's causing those particles to be deflected. Okay, so that is an example then of a magnetic field interacting with moving charged particles to produce a magnetic force on those charged particles. And then we like to put this thing back on when we're done with it, because thermal activity within these things can, over time, because of entropy, make the alignments of the different iron atoms less effective. So it loses its strength over time.
So does that just help, like, make sure they're in the same temperature?
Well, what it does is it, by completing the loop, it allows for magnetic torques to keep working against entropy and to keep the thing aligned. Okay, so here's our expression then for how the force works. But before I look at this in more detail, I wanted to mention that this kind of an expression is just the result, and it's not the real cause for magnetism. The real cause for magnetism is what's called relativistic contraction. If you, and this is something that I'm not likely to test you on in this class, but in Physics 2.8c, if you are running really fast with a meter stick, let's say, 98% the speed of light, what you'll see is a contraction of the length in the direction of motion. And that's called length contraction. And you also have a time dilation effect where clocks move more slowly on the meter stick, as well as length being contracted. And it also results, when you follow the math through, with E equals mc squared. That's also a byproduct of these relativity effects. And so, in a wire then, with moving electrons, they're just moving with a drift velocity, but relative to us, there's an increased charge density because their length contracted. And so I'm greatly exaggerating the length contraction here, but this is what we see. And this increased charge density caused by length contraction generates an extra electric field. And we call this magnetism. So this magnetism effect is actually due to relativity. And nobody knew about this when Maxwell was coming up with his equations of electricity and magnetism back in the 1800s. But when Einstein discovered this, he proclaimed that his theory of relativity was too beautiful to be wrong because it was predicting phenomena in other fields that didn't appear to have any direct relationship to special relativity. It turns out they did have a relationship to it, because the speed of light is actually the mutual induction of electric and magnetic fields that invents itself as it moves along at the speed of light. But there's this very close connection then between electric forces that we've been talking about and magnetic forces. So we'll treat these magnetic forces as if there's something different, but in reality, we can just keep it in the back of our mind that it's an extra electric field that is causing these forces. Okay, so given that, in chapter 28, we're not going to work too much with the source of the magnetic fields. We're just going to work with pre-existing magnetic fields in 28. And in 29, we'll figure out how to calculate them. That's kind of like what we did with electric forces. you started out saying, well, we'll just have an electric field here and not worry about what caused it. And similarly here, we'll say that there's a magnetic field, but we're not going to be too worried about what caused it. So where might we get this pre-existing magnetic field? Well, we could get it, for example, with a horseshoe magnet. You have something like this. And then this would be the North Pole, this would be the South Pole. And so in between, we might have little edge effects like this, but you'd have something that's kind of like our semi-infinite plane approximation for electric fields, in which the magnetic field is constant in this region between, this narrow region between north and south. Another place where we can get approximately constant magnetic fields is with the Earth. Surprisingly, the Earth has a magnetic field that's similar to what you would have if you put a bar magnet right in the middle of the Earth. And yet that's not what's causing this magnetic field pattern. But it's acting as if it were. And so if we get far enough away, say out here somewhere, in this region, the tangents to these curved lines are approximately parallel straight lines. So you could say far away from the Earth, the magnetic field could be thought of as approximately equal to a constant value. But just over small regions that, say, are away from this more global magnetic field pattern. And so those would be the kinds of problems we'll be looking at to begin with, just so we can get used to the whole idea of how to work with magnetic forces in general. And then we'll get more specific as we go. So what we can say then is that the magnetic force is a vector cross product that's equal to Q. This is the charge on the moving object. Times V, this is the velocity of the moving object. Times B, this is the magnetic field that the object is moving through. And so where did it come from? Well, it could be any one of these sources. We're not going to worry about that yet. We'll just state it as being a pre-existing magnetic field to start with. And so when we have a vector cross product, the magnitude of the force is going to be QVB times the sine of theta, where theta is the angle between V and B. Okay, so that's the magnitude of the force. How do we get the direction? Well, the direction comes from the right-hand rule. This is very important that you get this now and don't wait to try to figure this out. So I'll get this later. No. You need to get it now. Why? Because we're going to go through 20 or 30 of these examples, at least, before the next midterm. And what's happened in the past is that I have people coming up and saying, hey, I don't know how to do this the day before the exam. And it's like it's almost too late at that point. Need to, because that means you didn't understand any of those other examples. So this is absolutely critical to taking the next step, that you know how to do this right-hand rule. And we'll practice this a little bit in class today, just to make sure we can do it. Okay, so how do you do it? Well, what you want to do, and this is what we call the right-hand rule, and there's different ways of accomplishing this. There's actually 3 different ways that I know of, and the one that I like the most is this one. In this case, it's V cross B, but it could be any other variables too. In general, this could be some D cross E. Right? But for the kinds of forces we're going to be dealing with, what we need to do is figure out how to get the right direction from V cross B. So let's do this with a physical example. Say we have a charge Q moving with a velocity v, and let's say the magnetic field is into the board, a constant. Okay, so the way that I'll indicate that here is with tail feathers, because these are all 3-dimensional problems. So it means that we can't get it all on a plane. We have to think in terms of our viewing perspective in 3 dimensions. So an X like that means the field is into the board. So these are like tail feathers. If you get something like this, that's like an arrowhead. So that means the field is out of the board. So in this example then, say B into the board. And it's moving with some velocity V to the right. So what are our steps for getting V cross B? Step 1, take your right arm, make sure that, make sure everybody here has right arm. Take your right arm, point it in the direction of V. Then step 2, curl your fingers in the direction of B. Remember that V here is just the same kind of field that we were talking about with electric field. Take a tangent to it, then that's the strength of the magnetic field, just like it was the strength of the electric field. And all of those things about vector fields still applies for magnetic field. So we curl our fingers and point them in the direction of V. And then in step 3, unless you're a contortionist, just look at which direction your thumb points, and that's the direction of the force. So this is really super important. Now, you need to think in terms of, like, maybe have a little prop here, and that's what I recommend. And you want the vector tails to be together. So that's something that is really important here. Vector tails are together. So I've got V like this, and then I'm just gonna, you could do this with your pen, your pencil. I'm gonna put B like that. Okay, so this is V cross B. So we see which direction then my thumb is pointing is up. V this way, cross B, curling my fingers in the direction of B. B cross B. And so we could do that in any other orientation too. And that's why I like it better. There's another one that's like this, where we do your first three fingers. You can do V for your first finger, then B for your second one, in the direction your thumb points is the third. And some people like that one better. I don't like that one better because it's harder for me when I get into weird positions to visualize where I am. I kind of lose where I am. I used to work on my car all the time, and I would be under the car, and I'd be undoing a bolt that was up here. I'd always screw it the wrong way. So this is a way to keep me from getting confused. But if you like this one better, just do it the same way, whichever way you want to do it. But don't go back and forth between this way and this way, because then you're going to not be doing it consistently, and it won't be a good habit to develop. Okay, so this gives me a force then that's up. So that's the direction of the force. Notice that the force is perpendicular to the velocity. That being the case, that means that the force can't speed the object up. It can only change its direction. So it's a centripetal force. And this is the reason why a lot of magnetic forces that are felt by particles make them go round and round in circles. And that is the case with our Van Allen radiation belt that surrounds the Earth. The Earth has this protective umbrella from high-energy solar and wind particles. These particles are being evaporated by the sun, moving at relativistic speeds, but when they hit the Earth's magnetic field umbrella, they're turned into these circular paths and then deflected up near the poles to create the aurora effects. And so without that kind of a magnetic umbrella around the Earth, our atmosphere would have evaporated long ago, and we'd be getting blasted by radiation. So we're really lucky that we've got a good magnetic field on the Earth. None of the other inner planets have a good magnetic field. So it's just the Earth does. And so that's another thing that we have to be thankful for, the fact that we're here, is that we've got this magnetic umbrella that protects us. But anyway, getting back to this problem, let's actually plug in some numbers. Let's say that the velocity, v, is 10 to the 6 meters per second. Let's say the charge is equal to millicoulomb. And let's say the magnetic field is equal to 2 Tesla. Okay. Now, the units for a magnetic field are the Tesla. So that's given a symbol T. So if you plug in, force is equal to Q VB times the sine of theta. Then we have Coulomb here, meter per second. This is Newton. And so you could say that a Tesla then is a Newton second divided by Coulomb meter. Or you could break it down to more basic units, but as long as everything else is in MPS units, the unit for magnetic field is a Tesla. 1 Tesla is kind of like a farad. You know how 1 farad is like a lot of capacitance? 1 Tesla is a lot of magnetism. You go into an MRI machine and they tell you, take out all the coins from your pocket and your cell phone, you got to get that out of there, and because they'll put you through a couple of Teslas worth of magnetic field, and that would take anything that's metal. If you got a metal plate, you don't even go in there. because it's going to exert tremendous forces on it that could be dangerous. But they say at least that strong magnetic fields don't affect your health. And I'm inclined to agree with that, although I don't completely 100% believe it. But it does seem like there's a lot of evidence to show that really strong magnetic fields are damaging to the body. Okay, so in this problem then, the angle would be what? Between B and B? 90. So the magnitude of the force then would be 10 to the minus 3 coulombs times 10 to the 6 meters per second times B, which is 2 Tesla, times the sine of 90. And so that would just be 2,000 newtons. So that's a pretty large force that's being exerted, 2,000 newtons on that mass. And so then we could set that force, well, we wouldn't set it equal to the regular mass times acceleration, but we could set it equal to mv squared over r, because it's going to be a centripetal force that can create circular motions. And so that's the force in that situation. But what if it were negative? How would that change this problem? And go ahead and don't scream it out, but let's just change it to negative. How does that change the problem? Like keep all the numbers the same. Let's find the new force, magnitude and direction. Go ahead and do that. And don't just say, well, I think it's opposite. You know, go through the process, because this is where you get practice. Okay, is anybody done? Is everybody done? What's the difference? The direction is different. How did you get that the direction is different? That's correct.
I didn't finish calculating it, but the cross product would be opposite.
Okay, the cross product will give you the opposite direction. Here's a couple of ways of looking at it. One is that you've got a negative charge in here. So with the negative charge in here, whatever direction you got before using the right-hand rule was for a positive force and a positive charge. And so if this has something to do with extra electric fields, doesn't it kind of make sense that the force would be in the opposite direction? Because it would be down instead of up. Okay, and so if we have figured out what this direction is for positive charges, then we just reverse the direction of the force, and that's it. So that's all we have to remember, is reverse the direction of the force. Or, and I'm not recommending this, but you can use your left hand. Use your left hand, then you can do Q, V cross B, like this. Here's your B, and then you get a force that's down. Use your left hand, because your left hand is the mirror image of your right hand. But that being said, I don't do that anymore, because when I first was learning how to do this, I was all set for all of these different problems, and then I forgot which hand to use. And I started using my left hand. I was getting a bunch of problems wrong, because there were positive charges, I was using my left hand. So I always recommend, after that debacle, that you do it for positive charges, and then just remember at the end to reverse the direction. Okay, so let's see if that works for this problem that we were talking about here. Here we've got, I'd like you to try to figure this out on your own. I've got a magnet with a north pole on the right. Okay, so the north pole is on the right. But it's horizontal. I'm trying to give it some perspective here. That's right. That you're bringing this thing in, and then the velocity of the electron is coming out. So what's the direction of the magnetic field going to be here? This is north, and this is south. I'm bringing it in horizontal, like this. I'm bringing it in horizontally. I'm just trying to give it that perspective there, but it's coming in horizontally, parallel to the floor. So what's the direction of the magnetic field? It's going to go out of north and then back into south. So it's going in like this. Do you see how that is? I'm holding it like this, so it's going out and around and then back in. So can you see that it would be going this way? Here's the north. Got to get our three-dimensional thinking caps on. Here's our north, south. So it's going out like this, around, and then back in like that. Can you see that? Okay, so that's going from north to south. So it's going to the left. Okay, so if it's going to the left, and the velocity is out, then what direction are we expecting the force to be acting? Okay, so this is going to be V cross B, like this, right? So I'm going in the direction of V, out toward you. And then I'm curling my fingers in the direction of B, right? So this is V cross B. And so I'm getting a force that's down. Aren't you? This is, here, V, right? V cross B. Everybody seeing that that's a force that's down?
Wait, I'm confused because we're going from north to south, so we're going this way. So-
North to south. That's
Yes,
this way, yeah.
yes, but
North
then
to
we're
south. So
going
it's
the
to the left. This is V cross B. Of course, it's down. Here I bring this in and it's going up. We already saw that before. It's going up. Why is it going up? Because they're electrons, right? Negative charges. These are electrons that are moving, so that's why you change the direction. Okay, so it would be down if they were positive charges moving through here. But it moves up because they're negative charges.
So if you rotate the magnet, it would go down.
Let's do that. Turn it around like this. Now the north is on the left and the south is on the right. Goes down. Then if I turn it at some angle like this, then I can make it go at a diagonal. Because now the magnetic field is this way, and so then the force would be V cross B, and so that would either be up or down that way. It takes a little bit of getting used to just being able to visualize the three-dimensional perspective. Any questions so far?
Yes,
Yeah.
okay, so from the north to the south, that line, what does it represent?
That's the magnetic field strength.
Okay.
So the magnetic field is a vector. It's going from north to south. Just like the electric field was a vector going from positive to negative. This is our electric field. Went from positive to negative. Here our magnetic field, similar, goes from north to south. So we just need, if we can get a couple of those things straightened out and we can do that right hand rule, then we should be good to go on these problems. Any other questions so far? All right, let's go back and let's try a couple of these. I'll give you 4 of them. see if you can turn them around in your head and get the right force direction. Oh, by the way, before I do that, let's just do it at a different angle. Let's say that the magnetic field now is this way, and the velocity is this way. This angle here is theta. Let's say that theta is 30 degrees. And this is a positive charge, but now the magnetic field is at a 30-degree angle to the horizontal. Remember, that's going from north somewhere to south somewhere else. Just like with the magnet that we showed, where it shot off at an angle. Okay. So now we'll do V cross B. Okay, so now we're taking our hand, we're pointing in the direction of V, and now B, we're pointing your pen in the direction of B, and we're curling our fingers so we see that the force is out. How would that be different if we made this 90 degrees? It wouldn't be. What would change?
The magnitude.
The magnitude of the force would change, but the direction wouldn't change. If the magnetic field were pointed this way, then I would just still be doing V cross B, and that would be still the force that's out of the board. Now, you can forget everything that I said and still get a 50% chance of getting the problem right. If you just remember that the force is perpendicular to the plane of B and B. Okay, so here we have a plane that's defining B and B. So just from that rule alone, I can tell you right-hand rule means that it's got to be perpendicular to both vectors. That's what right-hand rule means, basically, when you do a vector cross product. Is that the third vector is perpendicular to the plane that's defined by the other two. So that tells us then that the force either has to be into or out of the board, and so if you're feeling lucky, you can just forget everything else that I said and just randomly guess. And you'll have a 50% chance of getting it right. Way better than Las Vegas has. Okay, so if this were the case then, let's say that V here was 10 to the 6 meters per second. B was equal to 1 Tesla, and Q is equal to 10 to the minus 3 coulombs. Then our force, F, would be equal to 10 to the minus 3 coulombs times 10 to the 6 meters per second times 1 Tesla times the sine of 30. So that would just be 10 to the 3 divided by 2, or 500 newtons. And that would be 1/2 of F max, where F max is gotten when theta equals 90 degrees. So in other words, we would have a maximum magnitude of the force when the magnetic field is completely perpendicular to B. Now, how does this work then if we're in the same direction? What if theta is 0? Then what's our force?
Also
0. What if the angle is 180?
0. Also 0.
Force is still 0. So if the angle between B and B is 0 or 180, there's no force. So it's not enough then just to say that you have a magnetic field that's produced by one moving charge interacting with another moving charge. That's not a necessary condition for a magnetic force. You also have to have some component of V perpendicular to B. you're forced to act. Okay, so with all of these different ideas in mind, and also remembering how to do the right-hand rule, and the fact that you've got to change the direction if it goes from positive to negative, let's try a couple of these problems. First one, let's say that the velocity is out of the board and the magnetic field is down, negative charge. Find the force direction. Two, here we have a charge moving to the right and a magnetic field moving to the left. The next one, let's have the velocity moving this way and the magnetic field going down like that at a 45-degree angle. And let's make this a positive charge. Finally, for these two, find the magnitude in terms of V and B. For all three of these. And then for number 4, let's say that the magnetic field is out of the board and the velocity say force is up. Yeah, that's what I want. Okay. The force is up, the magnetic field is out of the board. Find the velocity of the negative charge. Assume that the force vector and the magnetic field vector are perpendicular, and that this is and we'll assume V is perpendicular to B. Okay, so those are our 4. Go ahead and work on these. I'd like these also turned in with that thing that we do that you're doing with the RC circuit. When you turn that in on Friday. Turn this in too, please. All of a sudden, everybody's.
For number 1, coming out of the board is the velocity, right? Or is that the?
Yes, the velocity is coming out of the board here, and it's a negative charge.